Hello everybody, welcome to our class in geometry. Today in the end of chapter 5, we will be talking about quadrilaterals, medians, and bisectors. So what are they and how do they affect what we're doing? And we're also going to define them. For once, we are actually not going to have any theorems in this section. So hooray for those guys that are kind of like overwhelmed by those things. So anyhow, let's go ahead and get started. So first of all, what I did was I drew a bunch of pictures where these are possible quadrilaterals. Now, quadrilateral, first of all, from what you guys know before geometry, is that you have basically four segments or four sides. So you can see all of these pictures right here, they all have four sides. Now, the ones on the bottom are a little bit different than the ones on the top. The top, you can see they have a certain special characteristic, whereas the bottom right here, these are not considered quadrilaterals. And you can kind of see as to why they are because you never encountered them in the past. Now, for this last example, you're thinking to yourself, okay, well, this is a triangle. But in this case, what's happening is that we have four segments, and the segments are located right here, right here, right here, and right here. So what that means is two of the segments are actually collinear, and in that case, we do not consider it as a quadrilateral. So what I want to do now is I want to give a formal definition of the difference between the top part and the bottom part. What is a quadrilateral versus what is not a quadrilateral? So here we go. The first part we're going to say is that let's say that we have 4 points, A, B, C, and D. They are non-coplanar, so they all have to be, they have to be coplanar, so that means they all have to be on the same plane. Now, in addition to that, to avoid the bottom half, I'm going to go ahead and say that no 3 points are collinear. So then that way, they are not going to form some sort of triangle. And then finally, the segments AB, BC, CD, and DA only intersects at their endpoints. So then that way, once again, we're going to avoid the bottom row by having them intersect somewhere in between. Then the conclusion is the following then. The union of AB, BC, CD, and DA, all of those segments together, that's what's going to form a quadrilateral. And that is a picture of it that's on the right-hand side. So you can see how if I combine all of these together, that is going to form then my quadrilateral. There are specific names for each part of these. So the segments that form the quadrilaterals, that is what is known as the sides. And then if you look at just specifically the points A, B, C, and D, those are what is known as the vertices then. Exclude that angle D right there. So I apologize for that. Let me get rid of this small little part right here. It's just A, B, C, and D. Then we also have, if you look at the angles, A, angle B, angle C, and angle D, those are what is known as the angles of the quadrilateral. And then something that is not drawn in here, but we should actually draw it. AC, this segment right here, and let me just go use a different pen. AC, this thing right here, and also BD right here, that other thing, those are what is known as diagonals. Okay, so those are going to be the ones inside the quadrilaterals. And finally, for the last one, this is going to be the sum of all of the segments. So AB plus BC plus CD plus DA. If you add them all up numerically, that is what is known as the perimeter. The perimeter we'll probably not look at for another couple of chapters, but it's a good thing to just kind of introduce ahead of time. All right, so now that we got that stuff out of the way, let's talk about the types of quadrilaterals that you will encounter, or the ones that you have encountered already. The first one is a rectangle. So a rectangle is a quadrilateral where all the angles inside are right angles. So that's our formal definition for that then. Then, to be a little bit more specific, we say that a square is a rectangle where all the sides are going to be congruent to each other. So underneath, you can see the illustration between the two, the pictures of the two. The left-hand side, we definitely have a rectangle because all four angles are congruent and they are all right angles. And then whereas for the squares, you have all four angles are right angles, and in addition to that, the sides are going to be congruent to each other. So one can possibly say that a square is a subset of rectangles, which is a subset of a quadrilateral. So one is basically getting more and more and more restricted. All right, so now we're going to go ahead and move back into the triangle and then try to connect all these up together. The last set of definitions in here will be the following then. In a triangle ABC, suppose that D is the midpoint of AC and E is going to be a point that is on the opposite side, AC, such that ABE is congruent to EBC. So you can see that D right here on the triangle, that is going to be my midpoint. And E is a special location, not necessarily the midpoint, but such that ABE right there, that angle, is going to be congruent to this angle right here, EBC. Then we are going to define the following. BD, the segment that goes from the opposite vertex all the way to the midpoint, that is what is known as a median. And there are 3 of them because there are 3 medians you can possibly draw. Whereas BE, that is known as the angle bisector of angle ABC. And just like the median, there are 3 total of angle bisectors. Now, looking at the pictures, I drew it in a way so then that way you can see that there is actually a difference between the two, because one big misconception is that people think, oh, the way that the triangle is drawn, E and D must possibly be the same thing, meaning that if you have an angle bisector, that has to be the median, and that's actually not true. So the question is to you guys then is, when is a median the same thing as the angle bisector? And that's something for you guys to kind of discover on your own then, all right? All right, so here we go. Now we're going to go ahead and take everything that we did, and we're going to go ahead and look at a proof for a problem over here in the section. So first, we're told that we have a quadrilateral, and by the way, this thing right here, this little square thing, that is a representation that is a quadrilateral, not necessarily a square, nor is it possibly a rectangle unless it specially says so. So in this case, it does say that ABCD is a square. Then I have also PQRS are supposed to be the midpoint, and they are midpoints of those segments respectively. Prove that angle PQR is the same thing or is congruent to PSR. All right, so let's go ahead and maybe draw in some of the stuff in the figure so then that way it can help us out with the proof. So first, we say that ABCD is a square, so that means right off the bat, we can say that this guy right here, AB, is congruent to BC, is congruent to CD, and that's also going to be congruent to the last part, which is AD. Now, to be even more specific, because P, Q, R, and S are midpoints, then we can probably go a little bit further and say that these two right here are congruent to each other. And then these two right here are congruent to each other, and these two right here are congruent to each other, and these two right here are congruent to each other. Now, note that I use the same mark for all of them because the sides are all congruent to each other. So by transitivity, then I guess half distance segments are also going to be congruent to each other. So that is to say AP is going to be congruent to PB, which is congruent to BQ, all the way around. So then that way they're all the same. And finally, we're told that we have a square, right? And I didn't implement that, so I need to kind of go put that in there. Square means that we have right angles right here, right here, right here, and right here. Now, from the picture, what I want to do is I want to prove that PQR, which is going to be this angle right here, is supposed to be congruent to PSR, which is this angle right here. Well, looking at the pictures, I think you can kind of see what's going to happen here. We're going to prove that certain triangles are going to be congruent to each other. And according to the picture, it looks like it's going to be by SAS. And then that is going to tell me that those 4 triangles are congruent. Now, moving inward, the question is, how do I show those 2 angles inside are congruent? Well, maybe what I can do is I can introduce a line segment PR over here, so then that way we have 2 triangles to actually work with. According to corresponding parts, most likely then that means that this side is going to be congruent to this side, and then this side is going to be congruent to this side, and they're all going to be congruent to each other because of corresponding parts. Well, looking at those 2 triangles, I'd like to think that those 2 triangles are congruent to each other because they share PR over here. So in the end, what's happening is, if I were to kind of like write it out, the 4 side triangles we can prove to each other by SAS. And then moving inward, I can say that the corresponding parts of the inside are going to be congruent. And those 2 triangles inside would then be congruent by SSS. And that right there would then allow me to prove by corresponding part that the question mark on the left is then congruent to the question mark on the right. All right, so just like before, as always, you can always try to write the proof yourself just to see if you can do it. But that right there is going to be the outline of it. And if you want, you can go ahead and pause the video and try it for yourself. But if not, we're going to go ahead and move forward so you can see everything then that I've written up. All right, so here underneath, you can see that I have written everything out as we said. First, we're going to prove that the triangles on the outside are congruent by SAS. And the first part with the S, I had to be a little bit more meticulous about it because I want to make sure that I show the corresponding sides are congruent to the corresponding sides. So that took a little bit more work. But nonetheless, it's all there. So you can kind of take a look at it together if you want later on. Then I said the A part where I have the 4 right angles and 4 right angles are congruent to each other. So that is going to be the A part of my SAS. And then finally, for the last S, we're going to go ahead and pick the corresponding sides to each of the each of the triangles in the picture. So by SAS, those 4 triangles are going to be congruent to each other. And now, as we said earlier, once we say that the 4 triangles are congruent to each other, we move inward to say that those insides are going to be congruent to each other, meaning PQ, RS, and then SR, and then SP. So then that's going to be our next part. So we say specifically PQ is equal to PS and QR is equal to SR. And I'm just going to pick out the parts that I need because remember, I only need certain parts to prove the 2 triangles inside are congruent by SSS. Next, this part is going to be kind of new, so we're going to be looking into this in more in chapter 6. We're going to go ahead and introduce the segment PR because we technically never had that at the very beginning, right? PR was something that I had to introduce, so then that way we can see the triangle. The reason for that is the line postulate. If you remember, if you have 2 points, there exists exactly 1 segment that contains them. So whenever you want to create this line, that's where the line postulate comes in. Hey, there it is. Now that we have PR in there, I think I need to sneak in a small little step because I noticed I kind of missed it. So let me go ahead and cheat and call this 13.A. And I'm going to go ahead and say that PR is equal to PR by transitive, not transitive, by the reflexive property. Good thing I left a little space in between. But there it is. We're going to go ahead and say that that segment is just going to be equal to itself. So now we can say that the 2 triangles inside are congruent by SSS. And the corresponding part will then now show that the angles that I want are going to be congruent to each other. All right, so this is definitely going to be a lengthy proof. I never intend for anything to be over 10 steps, but unfortunately,